We're all waiting for provable, practical quantum advantage. How long until companies can start lifting and shifting classical computing tasks to quantum workloads? What are some of the most promising use cases to focus on today? And how can you win $1 million in the process? We're talking use cases in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of the post-quantum era. So our guest today is Pranav Gokhale. He's from a company called Supertech. That's Super.tech if you want to look him up. And we're going to focus today on near-term applications for quantum computing. So what other reason would we do something like this, right? Why else would we have a podcast about the post-quantum world if we're not going to look at ways that we could start benefiting as soon as possible? So welcome to the show, Pranav.
Hey, Konstantinos. Thanks so much for having me.
Yeah, great. I was really interested in what your company's doing. And there's all these like layers of abstraction to quantum computing, right? It's a full stack. It goes all the way down to like controlling qubits and all the way up to user-friendly interfaces for programming. So I don't know if you want to just give our listeners a little like high-level intro to your company and how you view where you fit inside that stack.
Yeah, for sure. So Supertech is spun out of research from University of Chicago, and we're also incubated by Argonne National Lab. And we come out of the computer science department. So one might think that we're just purely software folks, but we're sort of unique in that we're really paying a lot of attention to, like you said, the other layers of the hardware stack. And especially with quantum where it is today, when we have only tens of qubits and gate errors that are not 100, gate fidelities that are not 100%, we actually have to be very mindful of the interaction between the software and the hardware. And I think this is very similar to, say, the 1960s and the 1970s of classical computing, that is, anything that's non-quantum. Today, we have the luxury of Python programmers can write their software without ever interacting with the device physics of transistors. But in the quantum world today, we actually have to be more like the 1960s, 1970s programmers, where we have to manage memory. We have to manage the fact that there might be a bug in a literal physical breakdown in the electronics that could trigger problems in software. And so Supertech is a startup that's basically trying to abstract all that away, but also handle it. And we're reaching out to customers both in the hardware world who are trying to make their hardware behave better, and to customers in the application sector and finance and energy who are trying to get more mileage out of quantum computers.
Okay, so I almost thought for a minute there you're going to say a literal bug in a quantum computer. And of course, at these temperatures, that probably wouldn't happen, right? They probably wouldn't survive.
That's right. This is more of an analogy to Grace Hopper finding a bug while doing programming. But of course,
that would be an extremophile surviving in a refrigeration unit.
That's right.
So how would you partner? So let's say right now, the most common interface is this idea of like quantum as a service on the cloud. You know, very few people are buying one of these machines. It's this idea of you want to have a platform that people are comfortable using, and then they send their code to run on a simulator or an actual machine on the back end. And of course, the hope is one day that gets abstracted away, that you can just write code and it'll reach out to quantum computers as needed, sort of on the back end. So where would you fit in with something like Microsoft's Azure Quantum or Amazon's Braket, something like that?
Yeah, totally. So we are aiming to be very hardware agnostic, and we view these services that provide access to a lot of platforms as very complementary to our approach. And just as one example, so we're partnered with IBM right now, and also some other hardware companies through the Department of Energy. And the idea is that if someone is an energy company aiming to optimally allocate the power generation for the next 12 hours, they don't care if the answer comes from an IBM quantum computer or from a Rigetti quantum computer or et cetera. They just want the right answer. And so the stack that we're building is basically aiming to insulate, like you said, abstract away some of the nasty physics and bugs, so to speak, of the underlying quantum hardware and give an API and endpoint to customers that's very application centric. That is, find the optimal portfolio, find the optimal allocation of power generation units to turn on and off every day. So that's the sort of layer we envision operating at.
Okay, so you would try and have people write code that reaches out to you, and then you essentially would reach out to whatever backend hardware made sense.
That's right. Yeah.
Okay. And how do you make the decisions of what backend hardware? Do you then, based on certain types of applications, find that this machine works better than that machine? I know with, like, let's say IBM, you can go in and literally see, hey, this qubit's sort of like a bad qubit, it's less reliable. So certain machines just perform better in certain ways. Do you currently have anything like that set up where you decide what kind of hardware to reach out to?
Yeah, that's a good question. And in fact, we are launching something along this line this summer. And maybe to say a little bit more about where different hardware makes sense, I think a big divide right now in the quantum hardware world is between these superconducting machines like the IBM hardware that you described, and also these new trapped ion machines. And we take the point of view that it's not necessarily going to be like a winner take all market. They have different strengths and weaknesses. And most notably, superconducting quantum computers are very fast. They operate at the megahertz, gigahertz speeds. And that's really important if the client demands very short turnaround times, time to solution, if it's latency sensitive, say in finance. On the other hand, they have the disadvantage that error rates can be a little bit higher than, say, on trapped ion machines, which companies like Honeywell and IonQ are building. So these machines have advantages in terms of their qubits have very long lifetimes. They don't degrade as fast as superconducting quantum bits. The catch is that they're much slower. And so that's one dimension of many that informs our sort of decision diagram as to whether to route an application to a particular type of hardware that's, say, superconducting or to trapped ion. And in fact, there's a number of other hardware types that are upcoming, like photonic and neutral atoms. And they all have these different trade-offs. And we think that ultimately the end user shouldn't really care about making this decision as long as it gets the job done. And that's one thing that we're aiming to benchmark in the next couple months.
Yeah, that's great. And of course, there's more obvious choices too, right? If you want to go with annealing, really D-Wave's the only, game in town.
Right. Yeah.
So there are those solutions. And do you find that, I don't want you to reveal any customers or anything right now, but have you talked to any customers who are concerned with the whole concept of personal identifiable information or anything like that? Because when we talk to financial companies here at Protiviti, some of them still are a little sensitive about what they even would move to the cloud, let alone to a quantum computing interface. They're worried about where this is going to sit, how it's going to be handled along the way. Have there been any discussions around how to get useful high-speed interactions, like you mentioned, the financial low latency? Do they have any concerns about sending the data out through all these levels and then having it come back?
Yeah, that's a great point. And I've actually been wrangling with that a little bit the last couple of days. We're in the process of setting up our own cybersecurity compliance type issuances because of exactly this. What we do anticipate is that at least in the pilot stages, and to set realistic expectations, we're not expecting any sort of quantum advantage for some of these applications this year, though I'm pretty optimistic about the coming years. So I think in the interim, we're able to work with simulated data sets. And we also envision that there can be sort of client-hosted solutions that still run in the cloud from the quantum side, but you can really obfuscate the code in such a way that the end hardware provider really never learns about any sort of personally identifiable information. So that seems like one path. And of course, if it works out very well for a client, they might consider just buying the hardware outright. But right, in the interim, we're planning on working in the next year and 2 years with mostly anonymized data, aggregate data, simulated data, to just generally pilot and show that there could be an advantage with quantum technologies before we demand, say, person data. It certainly understood that customers be hesitant sharing that.
Yeah, the whole quantum advantage and supremacy kind of idea is still sort of a hot button. I like to joke around at the company that if you want to draw the ire and vehemence of the entire community, just say that you're close to achieving something like that. You're going to have people looking at you with a microscope. I guess in this case would be like an electron scanning microscope. But yeah. So how close do you feel we are to quantum advantage? I have some ideas, but because you see a lot of these companies, they put out these sort of extrapolations. They say that, hey, when we add this many features or whatever to a binary classification, you can see that a quantum computer will easily handle and scale up if you add a few qubits, but a classical computer will start to choke. So have you guys done anything along those lines of extrapolation where you can hazard a guess when you feel that we'll be seeing this advantage?
Mm-hmm. And of course, as you're aware, this is the $1 million question. And in fact, one of the quantum hardware companies, Rigetti, has literally put $1 million bounty on, if you run quantum advantage demonstration or hardware, we'll give you $1 million. And in fact, that's probably an underpayment because it would be such a big milestone. But we have some views on this. So, and knowing that this is also sort of an educational podcast, I might take a sidestep here to note that one of the things that I'm really excited about that has happened in the development of quantum algorithms is the invention of something called a variational algorithm. And in particular, it used to be that back in the 90s, the quantum algorithms that were envisioned were you sort of run it once and you get your answer. And instead, there's this new breed of algorithms that are more adaptive and variational in nature. So you don't just run it once, you run it dozens of times, in fact, probably millions of times. But what it does is it gives a lot of error resilience. And if I can give an analogy here, I sort of think of it as imagine your thermostat at home for heating and cooling is broken in such a way that it still works when you turn it right, it gets warmer, when you turn it left, it gets colder. But the actual knob is mistuned. It says that it's 80 degrees Fahrenheit and it's actually comfortable 72. So that's something that I'd consider very annoying, but it's not like end of the world. You can still just sort of recalibrate your expectations so that if you want it to be very cold, then it ends up showing, say, 70, which would seem comfortable, but actually it's colder and vice versa. And so that's the kind of resilience that a variational algorithm gives, is that the quantum computer itself can be sort of miscalibrated, but it doesn't really matter at the end of the day, because as long as you can turn the knob and left is left and right is right, you just sort of rebalance to a new point. And bringing this back to your question of quantum advantage, I think that with this variational algorithm paradigm, there's now hope for having quantum advantage before we have, as people may have heard, these error-corrected qubits. And so in one path where we need error correction, that's going to take millions of qubits to get to a quantum advantage. And that path will almost certainly happen, in my opinion, but I think it's 10 plus years away. I do think that sometime in the next 5 years or so, if error rates keep on plummeting the way that they are for current quantum systems, we can get away with not having perfect error-corrected quantum machines if we adopt these approaches like these variational algorithms. So obviously predictions are hard to make, but I would venture a guess that it's very feasible that in 5 years, with continuing hardware improvements and continuing co-design improvements with the software, that there will be an inflection point where it's more cost effective to run a problem on a quantum computer than on a classical computer.
Interesting. And of course, that'll still be subject to the comfort level of the companies that want to take advantage of advantage, right? Mm-hmm. Like right now, there are companies that do massive amounts of trading and things. And like I said, they won't even touch the cloud. So it will be that limitation of how can we get them to a place where they can take advantage of this quickly enough to have it be worthwhile and still trust, sending it out into the world, so to speak. So that's something we're trying to move them to.
That's right. And I was looking at the survey the other day that was surveying CEOs as to what kind of advantage they'd need to see for shifting to quantum. And it is the case that a lot of companies, they won't shift until that advantage, understandably, is like do or die, say 100x or something. And that first demonstration of quantum advantage, it's not going to be like an eye-popping do or die situation. It's going to be like, oh, it's 3% better. But of course, in an industry like finance or energy, that kind of margin could still matter in a lot of cases. And I think it'll be a gradual but accelerating pickup when it does happen.
Yeah, and there's lots of ways to sort of game the system, right? Like to come up with workarounds, ways that you can get little pieces of advantage, and overall make some kind of argument for still using quantum hardware from now.
Totally.
And it's been a while. Like it's interesting because there have been papers published on this field since around, let's say, 2015, where they're trying to show that you can predict a benefit, and that's always been an interesting idea. That like some of the first papers published around annealing, they showed that in theory we should be able to have a benefit, but they were still way far out. They were using like just a handful of qubits and trying to extrapolate. So I'm hopeful for things like trading execution and portfolio optimization that these will come along sooner than later. What would you say is your favorite of the use cases to work on right now? Like I like to lump them into three big groups. I think of them as optimization, machine learning, and pricing and simulation for the financials, let's say. Is there one that you find you're particularly interested in? It's like kind of your passion to see come to life first, something you're secretly betting on?
Yeah, I'd say those first two of optimization and machine learning. I like this categorization, by the way. This aligns with my worldview of quantum too. And in particular, I view both of those as sort of being selection problems in a way, unlike the sort of simulation forecasting model where it's more about like calculating risks and things like that. With selection problems, it's things like you have a basket of 50 stocks and you want to make a long short decision on each of them. Classically, of course, if you want to brute force that, that's 2 raised to 50 is a very, very large number. 2 raised to 100 is astronomical. And we don't expect that quantum computers are going to give an exponential speed up in these cases because of this whole P versus NP fundamental question in computer science. Mm-hmm. But we do feel pretty optimistic that in these sort of selection problems in the optimization sector, that is, given a basket of stocks or given a basket of resources that we want to make some binary or discrete decision on, make the best one that you can within a reasonable amount of computation time. And so that's an arena that I feel very excited about. It's, of course, fairly broad in the applications. And most importantly, with this selection nature of it, it's natural to fit it into the language of qubits, where 0 represents long, 1 represents short, or whatever for whichever industry we're in. And of course, with quantum computing, we can explore the superposition. And then in the machine learning sector, I think not quite selection problem, but there's these models called Boltzmann machines that you can sort of infer from the name that they sound very physics oriented anyways, but they were actually invented before quantum computers came to light. And now there's a lot of exciting research that suggests that even noisy quantum computers might be able to do a really good job of training these neural networks. So those are two that I'm particularly passionate about. We're actually working with both the government, Department of Energy and Air Force, as well as an initial customer that we'll announce soon on development along both these lines. And I'm also sure that Protiviti has been exploring interesting use cases in these spaces too. So perhaps sometime afterwards, we'll trade notes.
Yeah, definitely. And that brings up an interesting point with trading notes. So you're straddling government, you're straddling, let's say it might be a financial customer, it might not be, I'm not sure. How do they tend to feel about the work they are putting in being sort of available to the community, Like I still think of quantum computing as like a scientific advancement. I still put on that sort of like scholarly cap and think of it as like something that's going to benefit the world and we should be sharing as much as possible. But the reality is in the end, you get these companies that say, hey, if I come up with a great way to do something like credit scoring, I want to hang on to that, that gives me an advantage to pick the bad, prospects out and get rid of them. It might make my company do better. So How are you finding that your customers are right now? What stage are they in like in the altruistic kind of thought processes here? Are they thinking along the lines of sharing it all, or do they very much want to kind of like keep it to themselves?
Yeah, absolutely. So we ourselves and our customers wrestle with this question as well. And I think broadly in the next 2 years, I think it'll still be fairly quote unquote pre-competitive. That is, there's, as you point out, some degree of altruism. It's good for recruiting to share results and it's good for advancing the field. We can build off of each other. That being said, our customers and ourselves actually have selective desire to patent when there's some sort of secret sauce that we still will publish, but also want some IP around. It's naturally difficult to make an exact assessment of where that line is drawn. But in general, we coming from an academic environment are fairly pro open source, pro sharing with other researchers. And we try to find customers who at least want to release ideas, even if they still want to secure patent rights, but still put out the papers as opposed to purely doing like a trade secret type approach. That seems to be a happy medium in some regards. And in other ways, we'll go completely open source and open on other ideas that are hard to capitalize on anyways. I do think in the next, say, 5 years, that balance will shift a little bit more towards being very closed. In some sense, machine learning has followed similar parallels. But I think there will always be room for pre-competitive work through research collaborations with the government, research labs at the Department of Energy and universities and so on.
I wonder if we're going to see a drop off in the more scholarly papers soon. Like, will all those guys get snatched up? Guys and gals, will they be like pulled into like projects, and then it all of a sudden becomes very hush hush? And then I just don't want to see it drive to the point where the only papers being published are kind of rehashes of things from 5 years ago, and then that's where everything open source is stuck, and then it's all secret. Because right now they are all pulling from the same papers, right? If you think about it, all these IP kind of applications are still pulling from the same, maybe 60 papers that we've all read.
Yeah, that's right. And maybe to comment on another dimension here that I anticipate changing in the next few years. Right now, there's not much, say, federal interference if we publish our research. But there is a broader fear about the geopolitical aspects of this. Other countries are oftentimes taking US research and implementing it, not sharing it back in some sense. So I know that there's discussion about export controls and quantum, and there is both a fear and a very rational fear and hope about what this will mean in terms of academic publication. There may be sort of clearance approach where before publishing, there will be some sort of checks from the government. I think that's still a couple of years, 5 years down the road, but it's something that could happen, especially given the relevance of quantum to national security.
Yeah, it's fascinating because anytime you want to try and give an analogy for where we are in quantum, you end up having to evoke different decades in one conversation. It's like we're sort of in the supercomputing of the 60s, but in the crypto cypherpunk movement of the 80s, and we're in like machine learning maybe 5 years ago, and like you just keep having to bounce around from view to view. And
Yeah.
we have all those things to build on, all those past experiences. Are we going to make the same mistakes again, or will quantum come in with some maybe new set of eyes? It's kind of hard to say. I just would hate to squash the industry because of like silly old thinking, like outdated thinking.
Yep. We're also in like the 1700s with respect to training of a quantum workforce. So that's a priority that the government and stuff.
1700s,
Still a
yeah, I
little,
like that.
still a little behind.
We're right back to Babbage's analytical engine and seeing if there's anyone out there who can write a program for it.
Right, or the Greek Antikythera mechanism.
Yeah, just to throw in the late 1800s too.
Right.
Yeah, that's fascinating stuff. And we're going to be doing a workshop where we're going to try and pull together a bunch of financial customers, and we're going to see how much they're willing to share, in like an environment where they'll say, hey, I would like to see this, I would like to see that. And kind of a brainstorming session, we call it design thinking. And it'll be fascinating to see, how much will they share? Will they be comfortable sharing? And I hope to learn a lot about where their minds are, in these things. Because the more I talk to customers, the more I see they consider things proprietary that, sometimes you don't even realize.
Yeah, and I can see where they're coming from. It's certainly something that took me a while to understand how sensitive, especially customers in finance, can be about these things. It is encouraging to see that they're not complacent about the ramifications that quantum is going to have on their industry. And hats off to Creativity, by the way, for organizing this workshop. Excited to see how it'll go. I think I'll be attending that one too, by the way.
Oh, cool. Great. Yeah. And we hope to do more with other sectors too, like healthcare, maybe other industries. So it'll be fun. Hopefully a good lessons learned day. Mm-hmm. And so what do you think about surprises in the industry? Like, I feel like we've already had some. If you had asked me a couple of years ago how I thought the next 2 years would go leading to this point, I feel like in some ways we've exceeded my expectations. I really didn't expect there to be so many players in that like quantum as a service marketplace already, such a push to make quantum just another piece of a app development puzzle. And yeah. I just wonder, what do you think? Do you see anything coming soon that could shock us all? I mean, obviously there's topological quantum computing, the thing we've been waiting for forever. Will it happen? Won't it happen? That could change everything overnight. But is there anything that you feel like maybe scratching at the back of your mind might just change it all?
Yeah, good question. So I'll reminisce and say that I was giving a talk in, say, like summer of 2019 about when quantum supremacy might happen. It was to a bunch of MBA students. And I had said like, it might happen in the next 10 years or something. And then it actually happened a few months later. So that was one surprise that I was like, wow, this, because of really algorithmic innovations coupled with the existing hardware, we were able to get milestones much faster than expected. So that was really an exciting point for me. It's actually one of the impetuses where we decided to spin out our research to a company. So that's retrospective. Mm-hmm. But upcoming, I think one thing that I often wonder about is that the early adopters of quantum hardware, Google's, Rigetti's, and IBMs, say, they have all modeled on something called the transmon superconducting qubit. And it is a really good way to build a superconducting quantum system. But it was invented in 2007. And since then, better designs have come out that maybe require more control electronics. They're more expensive. But ultimately, when we're trying to get error rates down, there's this exotic qubit type called the 0-pi qubit. And it's starting to appear in some research. It's still not competitive with what, say, IBM has, the 50 qubit scale. But I think I'm looking forward to surprises in terms of what new hardware could come out that totally shocks everyone. It's not obviously the topological qubit, the holy grail could come out one day and that would leave everyone dumbfounded. But maybe more intermediate outcomes, or there's better ways of building superconducting qubits that are not on the current path of the big companies like IBM, Rigetti, et cetera, Google, but are in labs right now and really have a lot of potential. So yeah, to give a short answer, I'm excited about hardware that people are not really paying attention to at the scale of big companies, but in research labs are really starting to make breakouts. So that's what I'm super excited about, surprise-wise.
Yeah, that's great. And this idea of machines scaling up, a new technology can make that much easier, obviously, if you get lower error rates, et cetera. But every once in a while, a company will make some claims and, it takes a while to validate them. So whenever some of these surprises come up, you always wonder, will they follow through? Will they map it out? IBM made some pretty impressive claims recently. So their roadmap, they talk both about software and also hardware, but within a couple of years, we're looking at, over 1,000 qubits, and the way they're going to have their Qiskit environment working, hopefully a 100 times increase in performance, they claim, in the applications. So Do you have any reason to doubt their progress, or how's that looking to you?
Yeah, I definitely believe that IBM will put 1,000 qubits on a device. I think the question that really matters is, will they be 1,000 useful qubits? In fact, it's never been a challenge deeply to just add a lot of qubits to a system, but the challenge is adding qubits without degrading quality. And so I don't doubt that they could reach 1,000 qubits. I think it'll be an immense but attainable engineering challenge to do it while maintaining and in fact lowering the error rates. So that will be pretty exciting. I think that they have a good roadmap technically for doing it. So we've been collaborating with some of their engineers around the pulse level control of their quantum chips, as well as their algorithmic innovations in Qiskit. And I'm pretty optimistic about the IBM roadmap. In the past, they've actually done better than their projections. I think they were forecasting doubling of quantum volume every year. And in the last 1 year, they did 2 doublings. So still not that order of magnitude that you and I hoped for, but better than what they promised. So I'm pretty on board with the IBM roadmap. It seems realistic. I'm very excited to see what happens in the trapped ion world in parallel. IonQ, one of the companies that's big out there, and in fact was in the news because there was rumor about them going public at $2 billion through a SPAC. But anyways, I digress. They have allegedly a quantum volume of like 2 raised to 32 or something very, very large. So I'm excited to see how that will pan out. They haven't shown an official demonstration, which I think is why it's really important for other people to develop benchmarks. And in fact, stay tuned. We have a product launch around this in a couple months. But really an honest way to compare different hardware platforms, assess whether the company's claims in the PR release are really manifesting in terms of end user applications.
A benchmark is really exciting because for a while I've been thinking that quantum volume is probably dead. It just feels like with a little bit of tweaking, you can get a 6-qubit machine that claims a quantum volume of 4 million. And to me, that just doesn't feel right. I'm not sure that we're measuring it correctly, and at the very least in a way that's not confusing to people in the industry. So some kind of benchmarking that shows how everything is taken into account would be very welcome, in my opinion.
Yeah, right. And we're going to aim for application centric because quantum volume is like one way of building a circuit where it's very square in shape. That is the runtime of the circuit sort of equal to the number of qubits. But practical applications are going to be so much more heterogeneous that there will be some that have a lot of qubits and short runtimes, vice versa. So we're going to try to be much more application centric. And I think there's similar efforts out there amongst other companies too that hopefully will, by the end of this year, I think we'll be able to rely more on third parties to evaluate claims of hardware as opposed to the press releases from the big players every year.
Oh, that's really great. A bit of a surprise. I didn't know you guys were working on that. So I guess we could start wrapping up with that very optimistic note.
Sure. Yeah.
So is there anything you'd like to let our listeners know about before we close? Anything coming up maybe sooner than the benchmark?
We've got a workshop coming up more on the research side. So perhaps this is in conjunction with the Chicago Quantum Exchange really is driving this, but I'd really encourage anyone who's listened to this from industry to reach out to the Chicago Quantum Exchange, to Protiviti, and to Supertech if you're curious to learn more about where quantum is going in the next 5 years, how to develop a good strategy around using quantum applications.
Absolutely. Yeah. Chicago Quantum Exchange has been such a, just priceless partner here for my company. Yeah, definitely.
And I should also add P33. I guess you and I are both part of the quantum fellows of this organization for bringing more quantum industry to Chicago. So yeah.
Yep. I spend a good amount of time with those folks every week. Well, virtually, of course, these days. So yeah, and if anyone wants to learn more about your company, Super.tech, that's the easiest URL you'll ever have to remember. And thanks again, Pranav, for coming on. This was great. I really appreciate it.
Great. Nice to catch up, Konstantinos.
That does it for this episode. Thanks to Pranav Gokhale for joining today to discuss Supertech. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also find information on our quantum services at www.protivity.com or follow us on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.